Welcome to the deep dive. We're here to give you the most efficient path possible to getting your head around some really complex topics.
And today's is definitely one of those.
It is. Today, we are diving deep into the architecture of large-scale enterprise networks. And just to be clear, this is not beginner stuff.
No.
Our source material is all drawn from the concepts covered in the practice materials for the JNCIP-ENT certification. That's the JN0-650 exam, for those who know.
Right, but we're not here to help you cram for a test.
Exactly. Our mission is to strip away all that test anxiety and just extract the absolute core architectural insights. We're talking routing stability, advanced traffic control, and edge security.
You know, the things that define a network that can actually perform under pressure.
It's the gap between a network that just works and one that can scale globally and stay stable.
That's absolutely the right way to look at it. I mean, an exam like this, 90 minutes, 65 questions, it's designed to hit the non-negotiable best practices.
And the pressure points.
Exactly. We're not talking about how to configure a simple interface here. We're looking at the fundamental mechanisms that prevent entire networks from, well, collapsing under their own weight.
These details are everything. Okay, let's unpack this. Let's start with the heavy hitters, the big routing protocols, OSPF and BGP.
Let's do it.
Okay, so first up, a modern reality, IPv6. OSPF had to evolve, pretty significantly to handle it, which gave us OSPF v3.
Right.
And that shift forced a new architectural choice. So my question is, if we're talking about pure IPv6 prefix information inside an OSPF area, which specific LSA, or link state advertisement, is carrying that data.
Okay, so that critical piece of info is carried exclusively in the Type 9 LSA.
The intra-area prefix LSA.
That's the one.
So why is that so significant? Because in the old world with OSPF v2, the topology and the IPv4 address info were kind of tangled together in the Type 1 router LSA. Why did they explicitly decouple them in OSPF v3?
Decoupling is the perfect word. It's a huge benefit for scaling, a massive one. By putting the address information in that separate Type 9 LSA, you get so much more flexibility.
Okay.
The network can now update its addressing. Scheme-like, say you add a new subnet, without having to reflood the entire fundamental topology descriptor that's in the Type 1 LSA.
Ah, I see. So if I just change an IPv6 prefix on a router, the network only has to flood a relatively lightweight Type 1 LSA.
Exactly.
And it doesn't disrupt the core SPF calculation that's based on the much heavier Type 1 LSA. That sounds like way faster convergence.
It is. It makes the network far more resilient to just, routine administrative changes.
Yeah.
You separate the addressing from the topology, and that is a professional-grade design decision.
Brilliant. Okay, let's shift gears from an interior protocol like OSPF to the king of the exterior BGP.
The protocol of the internet.
It really is. And BGP relies on attributes to make its decisions. So which specific attribute is considered well-known mandatory, meaning it is absolutely non-negotiable? It has to be in every single BGP UPdate message.
That would be the AS path attribute, no question. It's the single most defining part of the route.
And when you say mandatory, what's the fundamental job it's doing that makes it so critical? Why can't BGP function without it?
It's the primary mechanism for loop prevention on a global scale. I mean, that's its whole reason for being.
Okay.
Remember, BGP is a path vector protocol. That path history, the list of the autonomous system numbers the route has gone through, is the core of the route. If a router sees its own AS number anywhere in that path,
Blocks it instantly.
It prevents a routing loop that could span the globe. And, beyond that, it's also the data you use for all your path selection policies. Without the AS path, BGP is just noise. It's like the network equivalent of a chain of custody for a data packet.
That's a great analogy. Okay, now here's where it gets really interesting, sticking with BGP stability, but let's look inside an AS.
Route reflectors.
Exactly. Architects use route reflectors to avoid that full mesh nightmare, but that creates a new risk: loops within the reflector cluster. So which BGP attribute is created by the route reflector specifically to stop those internal loops?
That mechanism is the originator ID attribute.
Originator ID. It sounds like a passport stamp or something. How does that ID actually prevent a route from just cycling around inside the cluster forever?
That's a good way to think about it. The originator ID is basically a digital signature that identifies the specific router that first advertised the route into the cluster.
Okay.
So when a route reflector sends out that route, it attaches this originator ID. Now, if any other router in that cluster gets a route that has its own router ID listed as the originator,
it knows it's seeing its own reflection.
Exactly. It knows the route has completed an internal cycle, and it just suppresses it. It's a safety stop. And it's what lets architects build these huge scalable designs without the insane overhead of a full mesh.
The genius is in how simple the solution is for such a complex problem.
It really is.
All right, that whole discussion was about how the network finds a path. Let's pivot now to governing what gets sent down those paths.
From routing to traffic quality.
Right. Let's start with multicast, specifically PM sparse mode or PMSM. When a receiver wants to join a multicast group like a video stream, which network component acts as that initial central root of the shared distribution tree?
That central coordinating point is the rendezvous point, the RP.
So why is the RP so important in sparse mode? Why can't the receiver just connect directly to the source from the get-go?
Well, the RP handles the discovery phase. In sparse mode, the sources aren't, universally known. The RP provides that one known, centralized point of contact for everyone.
It's like a meeting point.
It's the network's bulletin board for multicast, yeah. Receivers send their joins toward the RP, and sources register with the RP. That builds the initial shared tree. Only after traffic starts flowing can a router decide to switch to a more efficient direct path to the source, bypassing the RP.
That makes perfect sense. Okay, let's jump from there to the modern data center, EVPN. EVPN uses different route types for different jobs. So which EVPN route type is specifically designed as the inclusive multicast Ethernet tag and is absolutely essential for handling DUM traffic?
That would be EVPN route type 3.
And the architectural challenge here seems immense. In a traditional layer 2 network, BUM traffic, that's broadcast, unknown unicast, and multicast, is just flooded.
Yeah.
Everywhere.
A nightmare in a large fabric.
It would destroy performance.
Yeah.
So how does route type 3 solve that problem?
It enables controlled flooding. Instead of blindly sending BOM traffic out every single tunnel, route type 3 distributes signaling information. It tells all the other edge devices in that EVPN instance exactly which segments need the BUM traffic and how to replicate it.
So it's targeted.
Highly targeted. It makes sure essential things like ARP or DHCP still work because you need BUM for discovery, but it prevents that catastrophic traffic storm you get otherwise. Route type 3 is basically the rule book for necessary flooding in a big, scalable environment.
A mechanism for efficiency. Let's switch to quality of service then. Guarantees. When you're dealing with critical apps voice control traffic, you need an absolute guarantee of minimal delay. In Junos class of service, which scheduler priority level ensures a queue is serviced strictly before any other queue.
You are describing the strict high priority level.
So the moment any traffic shows up in that queue, it jumps the line. It gets all the bandwidth it needs, right?
Yeah, that is the design, yes.
Yeah.
It is always serviced before high, medium, or low priority queues, which is fantastic for things like voice. But this is also the most dangerous setting in CoS.
What's the inherent danger? What's the trade-off?
The risk is total starvation. If a strict high queue is constantly getting traffic, it can completely monopolize the output interface. It can starve even your mission-critical data sitting in lower priority queues.
Wow.
So the architectural requirement isn't just to enable it, it's to rigorously police the traffic before it ever gets to that queue. You need discipline to prevent your best intentions from crippling the rest of your network.
That tension between performance and fairness seems to be a recurring theme.
It's at the heart of good network design.
Okay, let's move to the edges of the network now. The physical and administrative boundaries. Let's start with the service provider problem. A provider needs to offer a customer a transparent layer 2 service, but they have to make sure the customer's own control protocols, their spanning tree, CDP, whatever, don't bleed into the provider's core network and cause chaos. What do they use?
They use layer 2 protocol tunneling, L2PT.
So L2PT is basically an isolation mechanism. It protects the provider.
Exactly. From a strategic view, the provider has to protect their own stability. A customer creating a loop must not be allowed to affect anyone else.
Right.
L2PT encapsulates those customer control protocols inside a special frame. The provider's equipment just sees it as regular data and tunnels it across their network. So the customer's control plane works perfectly end-to-end, but the provider's core stays completely safe.
Very cool. Okay, shifting to security at the access layer. We often use 802.1x, but a lot of devices, printers, cameras can't handle that.
Right, the so-called headless devices.
So architects fall back to MAC radius authentication. When they do that, what detail does the switch typically use as both the username and the password in that radius request?
The switch uses the client's MC address for both fields.
Why the redundancy? Why use the MC for both?
It's purely for validation. Since the device itself can't present real user credentials, the switch has to offer the server the only unique thing it has, the MES address.
So the Radius server just checks that MC against a list of approved devices.
Exactly. It's a pragmatic compromise. It's less secure than proper 802.1x, but it's necessary to get those non-capable devices on the network. You're trading security robustness for compatibility.
Got it. Staying at the edge, VoIP IP phones. How do switches automate the setup? How do they tell a new IP phone what the right voice VLAN is, what the layer 2 priority should be?
That automation relies on LLDP MAD, that's Link Layer Discovery Protocol Media Endpoint Discovery, specifically a container inside it called the Network Policy TLV.
So the Network Policy TLV is like an instruction sheet that the switch hands to the phone.
Precisely. It allows the switch to advertise the rules. It says, hey, your voice traffic goes on VLAN 500, and you need to mark it with Layer 2 Priority 5. This enables zero-touch provisioning for phones, making sure they get the right QoS settings instantly.
Which is vital when you're deploying hundreds of them.
Or thousands, yeah.
Yeah.
It eliminates so much manual work.
Okay, final one. Let's talk Layer 2 stability with RSTP Rapid Spanning Tree. Controlling the topology is crucial. If an architect wants to make sure a specific switch is the least likely to ever become the root bridge, what bridge priority value do they set?
They should set the bridge priority to the highest possible numeric value, which is 6, 1, 4, and 40.
That seems backward. Why does the highest number mean it's the least preferred?
Well, spanning tree is designed to be deterministic. It always prefers the lowest bridge ID, which is a combination of that priority value and the MSIC address. So to force stability, you find the switches that should absolutely never be the root, like a simple access switch, and you give them the highest priority value possible. By setting it to 64440, you make it the least desirable candidate in the election, which helps ensure your root bridge stays put on a predictable central core switch.
Thank you for guiding us through this. We hope this gave all of you the critical insights you needed into the genius behind modern enterprise networking.